Today we're going to start talking about some information about composite and prime numbers, and the first thing we need to take a look at is an item called number theory. Number theory is actually a branch of mathematics. Devoted to the study of the properties of natural numbers. And remembering then, of course, that natural numbers are our counting numbers, 1, 2, 3, and so on. One of the big ideas in this chapter, we're doing 2 sections in this chapter, is this idea of being divisible. So we say that A is divisible by B if there exists a value K such that A equals BK. And if B divides A, we write B, it's a vertical bar, and then A. Now, just to give you kind of an idea of what this looks like, let's take, for instance, the number 4. We know that 4 divides 20, and the reason is because there exists, that's a notation, so let's say it this way, there exists, a value 5, such that 4 times 5 equals 20. So that's the description that we've just created up here for divisibility. The next item is factor or divisor, which are interchangeable terms. If A is divisible by B, then B is a factor of A. So looking above, right, so if if 20 is divisible by 4, then 4 is a factor of 20, or a divisor of 20. The next, our next idea that we're going to look at is multiple. And a multiple, if A is divisible by B, then A is a multiple of B. Right, so if 20, well, let's see. Alright, so take for example that 20. So 20 is divisible by 4. So 4 divides 20, right? 20 is divisible by 4. That means that 20 is a multiple of 4. And if you remember back to your multiplication tables, that's what that would mean, right? That in the multiplication tables, or in the multiples of 4, the number 20 shows up, and it in fact does. Now, factorization is actually the process of breaking down a number into 2 or more of its factors. Now they may be prime factors or they may not, but any kind of factorization would include any kind of factors as well. So as we're taking a look, there's two different kinds then of factors. There are prime numbers and there's composite numbers. So prime numbers are the natural number that has exactly two different natural number factors. And those numbers are 1 and itself. Now, a composite number is a natural number greater than 1 that's not prime. And thinking along that idea, that means it has some other factor besides 1 and besides itself. So you could be thinking of the number, for instance, like 9. 9, of course, has factors 1 and itself, but it also has a factor of 3. All right, so we're going to take a look at some true-false questions about these ideas. The first one is, and decide whether or not they are in fact true or false. So the first one says there are no even prime numbers. That is, of course, false. Because 2 is both even and prime. Now, if we took this same question and we said there is only one even prime number, then that would be true because 2 is the only even prime number. And if you think about it, the reason is because if you took any other even number, it would have as one of its factors the number 2. That would make it not therefore prime. All right, the next one, 1 is the least prime number, and that also is false. Because by definition, prime numbers are greater than 1. But also it's false because 1 has only one factor, and it's supposed to have 2 distinct factors if it is in fact a prime number, and 1 doesn't have that. It only has itself as the number 1 as a factor. The prime number 53 has exactly 2 natural number factors, and that is true. It has 2 because it has itself in 1. Every number has 2 factors. And it's true that it has exactly 2 in this case because 53 is prime. And again, by definition, 53 or prime means that it has exactly 2 factors, itself in 1. Now we're going to take a look at looking at whether, or thinking about whether or not certain values are in fact factors of others. The first one that we're looking at is the 2. So divisibility test, a number is divisible by 2 if it ends in an even number. Okay, so if it ends in 0, 2, 4, 6, or 8. All right, a number is divisible by 3 if the sum of the digits of the number are divisible by 3. In other words, you can add all of the digits themselves individually, the individual digits in a number up, and if that sum is divisible by 3, then the original number is divisible by 3. A number is divisible by 4 if the last 2 digits are divisible by 4. And I don't mean individually, but I mean as a number themselves. So if the last 2 digits are 2, 4, then we would consider the number 24. And if 24 is divisible by 4, then the original number would have been divisible by 4. A number is divisible by 5 if it ends in a 0 or a 5. A number is divisible by 6 if it's divisible by 2 and 3. A number is divisible by 8 if the last 3 digits are divisible by 8. So 8 and 4 are very, very similar, and in fact, actually, they're similar to the number 2 as well. 2 has the last digit has to be divisible by 2. 4 has the last 2 digits divisible by 4, and 8 has the last 3 digits divisible by 8. 9 is very similar to the number 3. A number is divisible by 9 if the sum of the digits is divisible by 9. And then 10, a sum is divisible, or a number is divisible by 10 if it ends in a 0. And it's divisible by 12 if it's divisible by 4 and 3. Alright, so let's take a look at some of these. We're going to do an example of one, and we're trying to test whether the number has divisibility by the given values that we've just taken a look at. The first one we're looking at is the number 2. It is not divisible by 2 because it's not even. 3, if I add them together, the sum of my digits is actually 45. So 45 is divisible by 3. That means this value is also divisible by 3. So this one is a yes. Because the sum is 45 is divisible by 3. Taking a look at the number 4, this one is going to be a no. It's not going to work because the number 89, the last 2 digits, is not divisible by 4. And we actually know it's not divisible by 4 because it's already not even. I mean, we definitely have that information too. Alright, so let's do one more on this slide. The number 5. This one is not divisible by 5 because it does not end in 0 or 5. We'll do the number 6. The number 6, it is not divisible by 6 because it's not divisible by 2. 8, well, no, it's not divisible by 8 because the last 3 digits are not divisible by 8. Likewise, we could look at this one just like we did at the number for 4, is that it's not even, so it stands no chance of being divisible by 8 since 8 is even. We've got the number 9, so this one actually is a yes, because again, the sum is 49, I'm sorry, not 49, 45, and this is divisible by 9. 10 is a no, because it does not end in 0. And then 12 again is a no, and that one's because it is not divisible by 4. It's supposed to be divisible by 4 and 3, but it's divisible by 12.
My teacher said it was easy.
Alright, the last information we're going to cover in this section is the fundamental theorem of arithmetic. Now, this is fundamental in the sense that it's very important, obviously, but it's also fundamental in the sense that you use this all the time. You use this fact, whether or not you realize that you are using it or not. And here we go. This says that every natural number can be expressed in one and only one way, as a product of primes. And that is excluding the order. In other words, if you have 2 times 3 and 3 times 2, we don't say that's being expressed differently. The unique product of primes is called the prime factorization. All right, we're going to do one prime factorization problem at the end of this lesson. So we're going to take the number 300. I'm going to show you 2 different ways that you can find the prime factorization for the number 300. So one of them is a factor tree. And you may have seen this method before. We take the number 300 and we divide it by 2 items that would multiply together to give me 300. So maybe we choose 30 and 10. And then we keep going because neither 30 nor 10 is prime. 30 can be 10 times 3. And 10 is 2 times 5. And there's another 10 over here that's 2 times 5. The one thing that you have to be careful of when you're doing prime factorization with factor trees is catching all the ends of those branches. So the number 300 can be expressed as 2 squared, because there's 2 2's, times 3 times 5 squared. Now, this is kind of like when you were in English and you learned bubble diagrams and creative thinking, where you drew lots of pictures connecting your ideas together. That's kind of the factor tree idea of mathematics for this content anyway. Another one, and this one isn't necessarily called this, but I'm going to call it a division bar. And this approach kind of keeps things a little bit more structured, more like an outline would do in an English essay. So we're going to take the number 300 and we're going to divide it by the smallest prime that divides 300, and of course that is the number 2. If I divide that, I get the number 150. And then we're going to do it again. The number 150 is divisible by 2, and that's 75. Now, don't get carried away. I realize that 75 is divisible by 5, but it's divisible by 3 first, and we do go the smallest to the largest primes. So 75 divided by 3 is, of course, 25. Think money. 75 cents divided by 3 would be 3/4. And then 25 is divisible by 5 and 5. So the nice thing about this form is that all of your solutions are right here, sort of in a row. And they're all in order as well, so it's very easy to say, oh, this is 2 squared, because there's 2 2's in a row, right? Times 3, because it's the next one, times 5, and there's 2 of those because there's 2 in a row there as well. So either way, of course, you get the same solution, and it doesn't bother me. Whichever one you want to use is fine. It just kind of depends on how you think.